a coin tossed 4 times or 4 coins tossed at the same time will give you the same outcome. So what do you mean by event? Event is nothing but the subset of a sample space. So when I say subset, we are not going to write the entire sample space here. We are just writing the favorable outcomes. Then when I say A but not B, A but not B is nothing but A minus B. So what do you mean by A minus B? Only in A, not in B. Hello everyone, a warm welcome to one and all. This is your Shruti ma'am, Department of Mathematics. Today we are starting with the new chapter, Probability, that is the last chapter of class 11. Now here in this session, we are going to learn the introduction to probability, the events, also the types of events. We already know that probability is nothing but the measure of uncertainty. So that means, whether it may rain today, so it may be very hot tomorrow. So that uncertain events can be measured usually by a mathematical term called probability. So here, probability is a measure of uncertainty of various phenomena, and it is the ratio of the number of outcomes favorable to the total number of outcomes. So favorable outcomes to the total number of outcomes. So here outcomes is nothing but the results of an experiment. For example, when a coin is tossed, it may be head or tail, but both are called as outcomes here. Next one is the sample space. So the collection of all the outcomes of a random experiment is nothing but the sample experiment. Your science experiments like physics and chemistry will have a result which is only one. So if an experiment will have more than one results, then we call it as a random experiment which will be having more than one outcome. So therefore, the collection of all those outcomes is nothing but a sample space, and this is always denoted by S. For example, the outcome of an experiment of getting head or tail will be S, which can be written as H, T. The sample space of an experiment of a rolling a die. So we know when a die is rolled, we'll get 6 outcomes. That is 1, 2, 3, 4, 5, 6. So collection of all those in the form of a set is nothing but the sample space. And it is always denoted by capital S. Next one. Write the sample space for the following random experiment. So we are writing the sample space for the given experiment. 2 coins are tossed. So whenever 2 coins are tossed, so one may get head, the other may get tail. Both are heads, both are tails, like that. So that sample space can be written as, if the first coin shows head, the second coin may be head. If the first coin shows head, the second coin may get tail. If the first coin get tail, the second may show head. Then both can show tails. So these are the possible outcomes of an experiment. Next one, find the sample space of a rolling a pair of dice. When a die is rolled, the outcome is 1, 2, 3, 4, 5, 6. But when a pair of die is rolled, for example, if this is a die here, if I throw these 2 dice, one may show 1, the other may show 4. So like this, it may change its digits. So therefore, when you pair them in the form of a sample space, if the first die shows 1, then the second die may be 1 again, or 2, or 3, or 4, or 5, or 6. Or if the first die shows 2, the second die may change again, 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6. So depending upon the face value, so the outcomes changes here. Next it may be 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6. 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6. 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. So total there are 36 outcomes. So that we can write it as n of s. We know that n represents the cardinality of a set. So number of elements in the sample space is equal to 36. So therefore, for this experiment, there are 36 outcomes. Next one. A coin is tossed and a die is rolled. So when a coin is tossed, we have 2 outcomes. When a die is rolled, we have 6 outcomes. So when we pair them together, then we will get a sample space of the form. If the coin shows head, then a die may get 1 or 2 or 3 or 4 or 5 or 6. So therefore, H can be paired with the remaining outcomes here. Similarly, T can also be paired here. So thus these are the outcomes of the given experiment. Next one, a coin is tossed 3 times. So 3 coins are tossed. So one coin may get head, the other 2 may get tails. If the first coin gets tail, the other may get head, the other may get tail. So depending upon the face value, here also the outcomes can be written as all 3 coins may show head, or the first one head, second one head, third one tail. First is head, T, H, or T, H, H, or T, T, H, or T, H, T, or H, T, T, or T, T, T. So thus there will be 8 outcomes for this experiment. A coin tossed 4 times. That means a coin tossed 4 times or 4 coins tossed at the same time will give you the same outcome. So when a coin is tossed for 4 times, all the 4 times it will not give you the same outcome. So there will be a difference in the face value. So in the same way, when 4 coins are tossed simultaneously, they'll show up different values there. So it may be head for the some coin, it may be tail for the some coin. So depending upon that, if we write the outcome for this, then here we have H, 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 H. Next, there may be a sample space with 3 H and 1 tail combination. So H, T, H, H, T, H, H, T, H, H, T, H, H, H. Then 2 tail, 2 heads combination. So H, H, T, T, H, T, 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 H. Next we may get T, T, H, H. Then T, H, T, H, H, T, H, T, T, H, H, T. Then 3 tails combination. T, 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 H, T, T, H, T, T, H, T, T, H, T, T, T. Next, T, 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 T. So these are the required outcomes of the given experiment. Next one. 2 boys and 2 girls are in room X. 1 boy, 3 girls in room Y. Specify the sample space for the experiment in which a room is selected and then a person. First we need to select the room, either X or Y, then the person can be selected. So if I select the room X, then out of 2 boys or 2 girls, I can select any one. So now let room X contains 2 boys, let that be B1, B2, and the girls be G1, G2. Next, room Y contains 1 boy, 3 girls, so let this be B3, G3, G4, G5. So now we can select a room first. So X, then the person. It may be X comma B1 or X comma B2 or X comma G1 or X comma G2. If suppose I select room Y, then in room Y I can select again any one of the person. It may be B3, G3, G4 or G5. So these are the outcomes. This is the sample space. Next one. 1 dice of red color, 1 of the white color and 1 of the blue color are placed in a bag. 1 die is selected at random and rolled. its color and the number on its uppermost face is noted. Describe the sample space. So we have a die of red color, white color and blue color. So all of them are mixed inside one bag, and suppose if I take any one of them, let me take a red one. I have taken a red one. Now then I have taken a red one. Then I roll it. So the value which is written on the uppermost face should be noted. So if I select red, then it may show a value 1 or 2 or 3. Similarly, it can show 4, it can show 5, it can show 6. So these are the outcome for the red die. Now suppose if I choose white, then again it's the same combination with white. 3, 4, 5, 6. The same thing can happen with blue. 2, 3, 4, 5, 6. So thus here we have 18 outcomes. Next one, an experiment consists of recording boy or girl composition of families with 2 children. What is the sample space if we are interested in knowing whether it is a boy or girl in the order of their births? What is the sample space if we are interested in the number of girls in the family? So the first one says the order of the birth of 2 children. So if I take the sample space, the first one may be boy, the second is also boy. Or the first one may be boy, second is girl. The first one may be girl, second is boy, or both are girls. So these are the combinations which can be done, and hence we have 4 outcomes. The second one says we are just interested to know the number of girls. So number of girls may be 0 or 1 or 2. So these are the only outcomes, because when there are 2 boys, there are no girls, and hence it is 0. 1 girl combination and 2 girls. So therefore it is 0, 1, 2. Next one. A box contains 1 red and 3 identical white balls. 2 balls are drawn at random in succession without replacement. Write the sample space of the experiment. So when we have 1 and 3 white balls, we have 4 balls together. So if I take the sample space, I'll take out 1 ball which may be red, then the other has to be white. So I'm not putting it back, I'm taking out. So there are remaining 3 white balls. Obviously I need to select one of the white balls. Now if I choose the first as white ball, then we have 2 more white balls along with the red. So therefore it may be red or white. So therefore the only combination is W with red or W with W. So these are the only possibilities for the given experiment. Next one, suppose 3 bulbs are selected at random from a lot. Each bulb is tested and classified as defective and non-defective. Write the sample space for this experiment. So here it is like tossing the 3 coins simultaneously which have head and tail as a combination. Here the possibility is either it is defective or non-defective. So if it is defective, we'll write D. If it not, we'll write N. So the combination can be written as 3 bulbs where all are defective, or 2 defective, 1 non-defective combination. So that is DDN, D&D or NDD. Or 2 of them are non-defective, 1 is defective. That is NND or NDN or DNN combination. Or all of them are good. That is non-defective. So this is the possibility. So these are few examples we have taken to write the sample space of a given experiment with the possibilities. The next thing is we have event. So what do you mean by event? Event is nothing but the subset of a sample space. So when I say subset, we are not going to write the entire sample space here. We are just writing the favorable outcomes. For example, here, consider an experiment of tossing 2 coins. So what is the sample space? HH, HT, TH, TT. Now I create an event where the correspondence occurrence of exactly 1 head is what I needed. Then the only possibilities of getting 1 head is, one is HT, another one is TH. So that outcomes, I'll write it in one more set called E, and I'll write it in the set representation form, which is called as event. So clearly we can see here E is the subset of a sample space. For example, let me take one more example. We know the sample space of a die throwing experiment, that is 1, 2, 3, 4, 5, 6. Now I create an event where a die should get only an even number. So let me call that as an event E. So when I say it is only an even number, there will be only possibilities for 2, 4, 6. So no need to write 1, 3, 5 there. So clearly we can see here E is the subset of S, and E contains only the favorable outcomes, only the possibilities for what I have mentioned here. So these are called as events, and they are always subset of the sample space. Now, depending upon the condition of event, we have many types of events. The first one among them is impossible event. So when I say impossible event, there will be no outcomes for this experiment. For example, when I say, so an event containing a number less than 1 when a die is rolled. So we know that when a die is rolled, the sample space of the experiment contains 6 outcomes, that is 1, 2, 3, 4, 5, 6. But my event says I should get a number less than 1. Therefore, here it is empty. So that means the event does not contain any element here. Such events are called as impossible event. So therefore, it is empty. So remember, empty is also subset of a sample space, and hence it is also called as an impossible event. I can show you one more example here. So here we need to find out the outcome or a sample space of an event where it should be a prime number other than 2. So when a die is rolled, again we have all the outcomes from 1 to 6. Other than 2, there are no other prime numbers. So in such case also, the event E is empty. So therefore, empty sets in the probability are called as impossible event, and they are also subset of sample space. Next one is sure event. Here sure event is equal to the sample space. For example, the event consisting of a number less than 7 when a die is rolled. When a die is rolled, the sample space is 1, 2, 3, 4, 5, 6. Obviously, all the numbers are less than 7, and hence 1, 2, 3, 4, 5, 6 is again the sample space. So sure event is also called as the certain event, and hence it is always equal to the sample space. Next one, we have a simple event. Simple events are the events where you will be having only one outcome. Again, I can take an example of getting 2 heads when 2 coins are tossed. What is the sample space when 2 coins are tossed? That is HH, HT, TH and TT. So I want an event A where I should get 2 heads. The only possibilities is HH, and this event has only one outcome. So this is called as the simple event. So an event which contains only one outcome is called as simple event. Compound events which are not simple events, they are called as compound events. Next we learn about the algebra of events. The very first one is complementary event. We know that outcomes is all written under the sample space, and hence sample space will be considered as universal set for any random experiment, and all other events are subset of the sample space. When we have a universal set and its subset, we know its complementary also exists. Suppose I consider an event S of throwing a die, then the sample space will be 1, 2, 3, 4, 5, 6. Let A be the event of getting an odd number. So what is the event of getting an odd number in a die? That is 1, 3, 5. Then A complement is the outcomes which are not in A, and it is always S minus A. So when you subtract these two sets, you will get A dash, or we can say that A dash is a set or a complementary event which contains the outcome which are not in A. Which are not in A here? That is 2, 4, 6. And here A dash is called as the complementary event. Next one, the event A or B. So A or B is again A union B. So it's the same with respect to your set. If event A contains a number from 1, 2, 3, 4 and event B contains 3, 4, 5, 6, then A or B is A union B, that is all the elements in A and B. So this will be the union of two events. Similarly, we have the intersection also. If I take the same example with respect to A and B, so here AND is nothing but intersection. You can see we have 3 and 4 as common. So 3, 4 will be the outcome for the intersection. So OR is nothing but union, AND is nothing but intersection. Next one, the event A but not B. So it's like A minus B. Similarly, we can also write event B not A, which means B minus A. Suppose let the sample space of the experiment of tossing two coins is HH, HT, TH and TT. Let A be the event of getting two heads, that is HH. Let B be the event of getting at least one tail. When I say at least one tail, the possibilities are HT, TH and TT. Then when I say A but not B, A but not B is nothing but A minus B. So what do you mean by A minus B? Only in A, not in B. So only in A is HH only and HH is not in B. Similarly, we can write B minus A. That means only in B, not in A. So only in B means these three elements, they are not in A. So therefore, I will write HT, TH, TT. We can also write A union B. What is A union B here? A union B, write all the elements. So that is HH, HT, TH, TT, which is equal to the sample space. What is A intersection B? Do we have any common elements? No. So clearly it is empty. So these are all some operations which we do with the help of events here. Next one is very important, mutually exclusive event. If two events A and B are called mutually exclusive event, if the occurrence of one of them exclude the occurrence of another. For example, when a die is thrown, we know the sample space is 1, 2, 3, 4, 5, 6. So let A be the event of getting an odd number. So when I say getting an odd number here, obviously the even numbers are completely excluded. So which can be written as another event here, that is 2, 4, 6. So clearly the existence of one event does not disturb the other occurrence of another event. So clearly the existence of one event will not disturb the other and it excludes the remaining elements here, and you can clearly see here A intersection B is empty. So such events are called as mutually exclusive events. So therefore, when we are talking about mutually exclusive events, there may exist certain events for the sample space, but their intersection will be always empty. That means there will be no common elements between any two events when we say they are mutually exclusive events. So here, note that simple events of a sample space are always mutually exclusive. Obviously, it is true because simple events means which contains only one outcome. So the same event cannot be repeated again. So when we compare with the other simple event, obviously their intersection becomes empty and hence we can call them as mutually exclusive events. The next very important event is exhaustive events. So exhaustive events are many events which are the subset of a sample space. Suppose E1, E2, En are the subset of a sample space, then the union of all these events should be equal to the sample space. So consider the examples which we have taken here. So let A be the event of S and B be the event of S. Obviously, they are subset to each other. That is, A is also subset of S and B is a subset of S. And when we take A union B, that is equal to the sample space. So if the union of all events is equal to the sample space, then we call them as an exhaustive events. So note that the union of all the events from 1 to n. So there may be n number of events which are subset of a sample space, but when you take the union of all of them, then that should be equal to the sample space. Also, they should be mutually exclusive to each other. Suppose if A, B, C are there, whose union will give you the sample space, but their intersection with B, intersection with C, also B intersection C. If all of them are equal to empty, also that means they are mutually exclusive events together, then they are called as mutually exclusive exhaustive events. So mutually exclusive means their intersection must be empty. Exhaustive events means the union of all the events must be equal to the sample space. But when it happens so that they are both mutually exclusive and exhaustive, then we call them as pairwise disjoint. We call them as pairwise disjoint. Then such events are called as mutually exclusive and exhaustive events. So thus in today's session we have learned to write the sample space for a given random experiment and also learnt about different types of events. I'll meet you in the next session. Until then, keep watching, keep learning and keep exploring. Thank you.